Welcome to my workshop. I'm Jim. Today I want to share with you what I've learned about using NAND gates. A NAND gate will have a part number which includes 7400. Sometimes there'll be letters between the 74 and the 00, like this LS here, or the HCT in this one. Sometimes there'll be letters afterwards or even before. The two small X's in this number are used to mark the location of a character field which has not been specified, and which could be LS or HCT or any number of others. In the early days of integrated circuits, NAND gates were also made with the part number 5400. The 54 identifies the chip as being the same as its 74 counterpart, but capable of operating at more extreme temperatures and intended for military use. Finally, NAND gates are also manufactured with the part number 4011. These were part of the 4000 series of chips, which are manufactured using CMOS technology. The part number of a NAND chip will always include 74 and 00, or a 54 instead of the 74, or it will contain the number 4011. These chips all have DIP14 packages, which means they have 14 pins, arranged in two straight lines down both sides of the chip. There will be a dimple in the case above pin 1, and there will often be a notch at the pin 1 end of the chip. Like all DIP chips, these pins are numbered in the counterclockwise direction around the chip, starting from pin 1. In this case, pins 1 through 7 run down one side, and then pins 8 through 14 run up the other side. AND logic is something you learned about in school. Note that I'm referring now to the basic AND function and not the NAND function. There are two inputs to the AND function, either of which can be true or false. If one of the inputs is true, the other can be true or it can be false. If the first input is false, the second can still be either true or false. There are therefore 4 and only 4 possible combinations of inputs. The two inputs combine to make a single output. If both inputs are true, then the output is true. If either one of the inputs is false, then the output is false. This includes the case when both inputs are false, in which case the output is still false. This is the symbol used for an AND gate on a schematic diagram. The rounded nose is the distinguishing characteristic. The two inputs enter on the flat side, and the AND output comes out the nose. Of course, electric circuits don't run on true and false. They run on voltage. The real AND gate chip has a lead for ground, which will be connected to the circuit ground. They also have a lead which will be connected to the power supply. I've shown this gate operating from a 5-volt DC supply. In an electronic circuit which uses digital logic, things are arranged so that the voltage level is either 0 or the power supply's positive voltage. 0 volts represents false. The positive voltage, 5 volts in this case, represents true. For this circuit, we would revise the truth table as follows, putting in 5 volts for true entries and ground for false entries. The truth table now represents real voltages. Suppose we connect a voltmeter between the output pin and ground. When the AND output is true, the voltmeter will read 5 volts. When the AND output is false, the voltmeter will read 0. Logic chips are available which can run on other voltages as well. 5 volts and 12 volts are by far the most common, but you will also see 9 volts and 3.3 volts. The voltage used in a logic circuit will usually have been determined by other requirements imposed on the designer. In a 12-volt circuit, the truth table would be updated to show true entries as 12 volts. Since the particular voltage level is not an essential part of how the logic works, it is customary to restate the truth table once again, this time using high and low to represent the voltages. In fact, it is not even essential that the low voltage be the circuit ground, although that is the usual case. For reasons I will explain below, AND gates are not nearly as widely used as NAND gates. The NAND logic function is derived from the AND function as follows, starting with exactly the same truth table. To transform from AND to NAND, the output value is inverted. High becomes low, and low becomes high. In fact, NAND is short for not AND. When somebody talks about inverting a logic signal, that's what they mean, that high becomes low and low becomes high. This is the symbol for a NAND gate as it would be drawn on a schematic diagram. Its distinguishing characteristic is the small circle between the rounded nose and the output pin. The small circle represents the inversion of a signal from high to low or from low to high. You will often see these small circles at output pins and sometimes at input pins as well. It has the same meaning in every case, namely that the voltage at that point is inverted. Like AND gates, NAND gates will also have leads for the circuit ground and for the power supply. I've shown this one powered by 12 volts. I use the following trick to remember how signals flow through a NAND gate. Work from left to right. Combine the two inputs using the normal AND function, so the output is high if both inputs are high, otherwise the output is low. Then run the voltage through the little circle, inverting it as you go. This is going to be the pinout diagram for a 74HC00 NAND chip. Pin 7 at the far end down from pin 1 is the ground pin. Pin 14 across from pin 1 is connected to the power supply. This arrangement with the ground pin at the far end from pin 1 and the power in across from pin 1 is found on almost all small and medium-sized dip chips. Pins 1, 2, and 3 constitute a NAND gate. Pins 4, 5, and 6 are another NAND gate. On the other side of the chip there's a third gate using pins 10, 9, and 8, and a fourth chip using pins 13, 12, and 11. That's right, the chip contains 4 NAND gates. They are entirely separate. Each carries out its own logic function without any reference to the other 3 gates on the chip. It's customary to identify the 4 gates using small letters, from A through D, applied in counterclockwise order around the chip. When the chip is drawn on a schematic diagram, all 4 NAND gates will be drawn separately. On a schematic, logic gates are usually identified with names starting with the letter U, such as U3. The individual NAND gates on this chip would then be shown with the names U3A through U3D. The ground and power pins, pins 1 and 14 respectively, only need to be shown on one of the 4 gates. That gate doesn't have to be gate U3A, but could be any one of the 4 gates, like this. The particular gate which is chosen to be associated with the power leads is usually a matter of finding the least cluttered area on the schematic diagram. Let's wire up a NAND chip to show the basic operation. To begin with, I will use only gate B. I won't use the other 3 gates. Ground pin 7 will be connected to the circuit ground. In previous tutorials, I've used a 2S LiPo battery to provide the power. It has a nominal voltage of 7.4 volts. Suppose I connect it to pin 14. Pow! Well, that blew up the chip. There's a very tight restriction on the supply voltage for chips in the 7400 and 5400 series. The supply voltage must be 5 volts. There's a bit of leeway, say between 4.5 and 5.5 volts, but 7.4 volts will destroy the chip. I will therefore connect the breadboard to a desktop 5-volt power supply. An LED is a handy way to observe the voltage at the output pin. The voltage drop over the LED when it's lit will be 2 volts. That will leave a 3-volt drop over the resistor. 5 milliamps would be a good level of current to light up the LED. We can use Ohm's law to calculate the value of the resistor, which will drop 3 volts when 5 milliamps flows through it. This resistance is the voltage drop divided by the current. 3 volts divided by 0.005 amperes is 600 ohms. I will use a 510 ohm resistor in the breadboarded circuit. Now, what about the inputs? I could simply use wires to connect the input pins to the positive or ground strips on the breadboard as required. Instead, I will go with quality and use push-button switches. This shows how a push-button switch can be used to control how a high or low voltage is applied to one of the input pins. Let's push down on the push button, which closes the contacts. This will physically ground input pin 4, which will therefore be at logic low. Closing the switch also grounds the bottom end of the 10K resistor. We can use Ohm's law to calculate how much current will flow through this resistor when the switch is closed. Ohm's law is that the current equals the voltage divided by the resistance. In this case, we have 5 volts applied over 10,000 ohms, so the current will be 0.5 milliamps. In a sense, this is wasted power. In this configuration, with the switch closed, the 10K resistor doesn't do anything useful. It comes into play when the push-button switch is released. The contacts will no longer be connected. We can therefore entirely ignore the left-hand part of the switch, which is no longer connected to this NAND gate. It would be easy to conclude that the voltage at pin 4 is now high, since it's connected to the 5-volt power supply through the 10K resistor. While that's true, the reason is a little more subtle. We need to take a look inside the NAND gate. This is an enlarged copy of gate U1B. The circuit inside the chip contains a lot of components. Their net effect is that pin 4 is connected to the chip's ground pin, that's pin 7, through a very high resistance, which will likely be 10 megohms or more. So there is a pathway through which current can flow through pin 4 and into ground. The blue arrow shows this pathway. The current I, which flows through this pathway, has to pass through the series combination of the external 10K resistor and the internal 10 meg resistor. We can use Ohm's law to calculate the magnitude of this current. The current's equal to the voltage drop divided by the total series resistance. 5 volts divided by 10.01 megohms is 4.95 microamps. That's just under 5 millionths of an ampere. Because the internal resistance of the NAND gate is so high, only a very small amount of current flows into pin 4. So, what is the voltage at pin 4? We can find this using Ohm's law a second time. This time we'll use Ohm's law to calculate the voltage drop over the external resistor. I've shown the voltage drop in red. Voltage equals current times resistance. For this calculation, the current is 4.95 microamps and the resistance is 10K. The resulting voltage drop is 0.0495 volts. That's quite small, about 50 millivolts. Since that's the voltage drop over the 10K resistor, then the voltage at the bottom end of the resistor will be 5 volts minus 50 millivolts, or about 4.95 volts. That's very close to 5 volts. It's close enough to 5 volts that the NAND operation inside the chip will treat this input as high. Just to recap, the 10K resistor will hold pin 4 high unless the push-button switch is pressed and pulls the input down to ground. It's now a simple matter to add a similar push-button switch to the other input pin. Before proceeding, I need to make 2 more additions to the circuit. Firstly, I'm going to add a capacitor as close as possible to the power supply pin. This capacitor helps to protect the chip from noise. Electrical noise consists of fluctuations in current and voltage which race through a circuit when things change. It always takes a bit of time for a circuit to settle down after something changes. This is particularly important for digital circuits because the changes which do happen are sudden jumps in voltage from one extreme to the other. These are extreme changes, and they can cause spikes in current and voltage through any components or subcircuits which share the same power supply. A 0.1 microfarad ceramic capacitor will do nicely in most cases. When the power to the circuit is first turned on, this capacitor will charge up to 5 volts. Thereafter, whenever the chip experiences a sudden demand for current, such as when the LED turns on, this capacitor is a convenient and nearby reservoir of charge to smooth things over. Secondly, I'm going to eliminate all floating inputs. A floating input is an input pin which is not connected to anything. As things stand, there are 6 floating inputs in the circuit. Think back to the truth table for a minute. An input to the NAND function has 2 possible values, high or low. There's no third choice. There is no unknown or not connected. Many circuits act unpredictably if they don't have definite input voltages. I previously described the 4 gates inside a NAND chip as operating independently from each other, but that's not true if there's a floating input. A floating input can cause the gate to interfere with its neighbors on the chip. Since pins 12 and 13 are adjacent to the power supply pin on the chip, it probably makes sense to connect them both to pin 14. Floating pins can also be fixed by grounding them, like I've done here for pins 1 and 2. But floating pins don't have to be connected to a constant voltage, just to a voltage that's definite. For example, I'm showing pins 9 and 10 connected to the output of gate U1A. All that matters is that all floating inputs be connected to something which has a deterministic voltage. Don't be troubled about wasting gates in this way. Remember that these input pins were left floating in the first place because they weren't needed in the circuit. If they had been needed, they would have been used and wouldn't have been left floating. This is the completed circuit, which I'm now going to wire up on a breadboard. And here's the breadboard with the circuit wired up. This is the NAND chip. This black wire connects pin 7 to ground. This red wire connects pin 14 to the positive power supply. This is the 0.1 microfarad capacitor. Note that current which flows into pin 14 has to pass by the top end of this capacitor, giving it a chance to process spikes. Pins 12 and 13 are tied high by these two red wires. Pins 1 and 2 are tied low through these two black wires. The output from gate A is carried by these two orange wires over to the two inputs of gate C. This is the 10K resistor and the push-button switch for input pin number 4. This is the 10K resistor and the push-button switch for input pin number 5. The output of gate B is carried by this green wire over to the left end of this 510 ohm resistor. The LED connects the other end of that resistor down to ground. I'll now turn on the power supply. Neither switch is pressed, so both input pins are at a high voltage. The output from the NAND function is low, and the LED is off. I'll now press the left push-button switch. That now grounds input pin number 4. The output from the NAND function is high, and the LED lights up. Pressing the right push button grounds the other input pin of gate B. The result is the LED lights up. When I press both push buttons together, then both inputs are grounded, the output from the NAND is high, and the LED turns on. Everything works the way it should. How low is high and how high is low? Alice in Wonderland would say, high is high and low is low, and never the twain shall meet. But that's not true for electric circuits. An analog voltage is one that goes up and down all the time. The voltage waveform of some music in a set of headphones might look something like this. During an especially loud note, the voltage might get close to the positive supply voltage. During a quiet period, the voltage might drop down all the way to 0. The voltage in a digital circuit should look completely different. Ideally, it would be high or low, either at the positive supply voltage or at 0, as shown in blue. But that's unrealistic. Even the best digital circuit contains a bit of resistance, and the capacitance and inductance throughout the circuit will cause the voltage to be less than ideal. The voltage will oscillate. At times, it might even overshoot the high and low levels of the power supply. NAND gates deal with this uncertainty by using an exclusion zone. An input pin of a NAND gate will have two voltage thresholds, which I've shown here in red. If the voltage applied to the pin is less than the lower threshold, in this yellow region, the NAND function will treat it as being in the low state. On the other hand, if the applied voltage is above the upper threshold, in the upper yellow region, then the NAND function will treat it as being in the high state. There's an exclusion zone in the middle, which I've rendered in gray. If the applied voltage is in here, then the voltage at the output pin cannot be relied upon. It may be high or it may be low, but it might not be the NAND combination which the designer planned for at this point in the circuit. It follows that the output from a NAND gate will not flip its state at the same instant that one of the input pins passes through the midpoint voltage, which is 2.5 volts in this circuit. It's useful to take a look at what typical threshold voltages are. I'm now showing an extract from the datasheet for the 74HCT00 chip. Note that the power supply voltage must be within 10% of 5 volts. Figures are given for 3 temperature ranges. From left to right, they are room temperature, which is 25 degrees Celsius, an industrial range from minus 40 degrees to plus 85 degrees, and an even wider range from minus 55 to plus 125 degrees. I've circled the parameter described as minimum high-level input voltage. This is the upper threshold I described before. It's the lowest voltage at an input pin, which is guaranteed to be interpreted as high. That voltage is quoted as 2.0 volts across all three temperature ranges. The next parameter is the maximum low-level input voltage. This is the lower threshold I described before. It's the highest voltage at an input pin that is guaranteed to be interpreted as low. That voltage is quoted as 0.8 volts. I've now redrawn the threshold voltages and the exclusion zone at the 2 volt and 0.8 volt levels read from the datasheet. These may seem unusually low, but they're typical. Now I want to clarify something I said a moment ago. This chip does know what to do if an input voltage is equal to the midpoint 2.5 volts. It will always be interpreted as high. Everything shown here applies to voltages at the input pins. Something similar applies to the output. The voltages at the output pin will also fall short of the ideal. They have thresholds and an exclusion zone as well. The question is where they are. The datasheet shows that a high output is guaranteed to be 3.7 volts or more. This guaranteed voltage varies a little with temperature and with the amount of current the gate produces, but it is always 3.7 volts or more. The low side threshold is quoted as 0.4 volts. Once again, this voltage varies a bit with temperature and current, but it will always be 0.4 volts or less. 0.4 volts is the worst case low voltage. Note that the exclusion zone for the output is wider than that for the input pins. It had better be. This chip would be of little use if the output voltages produced by one gate were outside the limits another gate on the same chip used to discriminate between high and low. Since the voltages in a logic circuit are always high or low, or supposed to be high or low, it's easy to forget that a NAND gate is like all other electric circuits in that it must deliver power to the components which follow, and there is only so much power that a NAND gate can deliver. Suppose the output pin drives a resistor. This is something like the LED and its current limiting resistor we used on the breadboard. When the output voltage is low, there's no current since both ends of the resistor are at ground potential. But when the output voltage is high, current flows out of the pin through the resistor and into ground. In this condition, the NAND gate is the source of the current. It is said to be sourcing current. The 74HCT00 chip can source 25 milliamps of current. Now consider the configuration in which the gate is connected to the bottom end of a load resistor whose top is connected to the power supply. When the gate's output voltage is high, no current flows through the resistor since both of its ends are at the same high voltage. But when the gate's output voltage goes low, current will flow down through the resistor and into the output pin. The output pin is a sink for the current, and the gate is said to be sinking current. The individual gates in the 74HCT00 chip can sink 25 milliamps of current. Unfortunately, this ability of the 74HCT00 chip to source or sink 25 milliamps is overstated. To be fair to the datasheet, it does say that 25 milliamps is the absolute maximum current. Absolute maximum is an important qualification. The real value of the useful source and sink currents is only 4 milliamps. These are the maximum currents at which the exclusion zone I described above is guaranteed. If the gate is forced to source more than 4 milliamps, then the output voltage will fall below 3.7 volts. If the gate is forced to sink more than 4 milliamps, then the output voltage will rise above 0.4 volts. Note that the circuit on the breadboard used this chip, a 74HCT00, and that we designed the LED branch to run on 5 milliamps. It turns out that we were forcing the chip to operate a little bit outside of its comfort zone. This is where the letters in the part number, between the 74 and the 00, become important. They're an acronym for the type of construction of the circuits inside the chip. They can be used as a rough guideline for its ability to source and sink current. This table shows several examples. This is the 74HCT00 chip we've been using. There are other chips like the 74ACT00 which deliver more. It can source or sink up to 24 milliamps. Other chips deliver less and may even have different limits on their ability to source or sink currents. Before you rush out to buy the ACT variant, bear in mind that a high output current is not the only reason for buying one chip instead of another. These variants, as well as all the others you'll see in an online store like DigiKey, have other characteristics a designer could want. Now let's try a design example. Suppose we use one of the NAND gates in a 74ACT00 chip to control a small relay. This is a single-pole relay, meaning that it has only one set of contacts. I've not shown any of the details of the circuit which this relay controls, but I've represented that circuit with a blue loop. The relay contacts will act like a switch in that circuit, whatever it is. The NO between the relay's contacts, pronounced NO and not no, mean that the contacts are normally open. The contacts close and make a short circuit only when the coil of the relay is energized. Closing the contacts will complete the external circuit and allow it to start doing whatever it is supposed to do. At this point, we are only focused on how to operate this relay and how to cause its contacts to close. The relay is connected to the NAND gate so that current will flow through the coil when the output voltage is low. When the NAND output is high, the voltage at both ends of the relay's coil will be 5 volts, no current will flow, and the relay contacts will stay open. The parameter we need to know about the relay is the resistance of its coil. The datasheet, or perhaps the package the relay came in, will set out the resistance. Suppose the datasheet tells us that the DC resistance of the coil is 50 ohms. If you are just learning about coils, you'll already know that one of the important properties of a coil is its inductance. When the voltage applied over a coil changes with time, the inductance is the key measure of how the current will change. But in our case here, the applied voltage is a constant. The current flowing through the coil will also be a constant, or at least it will be constant after a very short period of time during which the inductive effects take place. This 50 ohm resistance is the resistance of the copper wire used to wind the coil. The wire will resist the flow of DC current in the same way as a normal resistor. We can therefore use Ohm's law to calculate the current which will flow when the NAND gate's output voltage goes low. Ohm's law gives the current as the voltage drop over the coil divided by its resistance. Here, 5 volts divided by 50 ohms is 0.1 amperes, or 100 milliamps. As powerful as the 74ACT00 chip is, its gates cannot sink this much current. However, there is a trick which can sometimes help out. What if we wire all 4 individual NAND gates in parallel? One of the main inputs is connected to one of the input pins on each gate. The other main input is connected to the other input pin on each gate. When they all work together, with each gate sinking the maximum current of 24 milliamps, then the combined current flowing through the relay's coil will be 4 times 24 milliamps, or 96 milliamps. That might be just enough to energize the coil and close the contacts. Wiring gates in parallel like this can be done if it's done sparingly, but it's not a very good design practice. It would usually be better to use a transistor in circumstances like these. The NAND gate would control the transistor, and the transistor would in turn control the relay. I need to tell you about propagation delay. Once you move past the most simple logic circuits, you will encounter it, and it will likely lead to tears. This little circuit has only one input and only one output. It's built from 2 NAND gates. Their make and model don't matter. Both input pins of the first gate are wired together so that it acts like an inverter. If the input voltage is high, then the AND function combines them as high. When that signal passes through the inverting circle, it will become low. On the other hand, when the input voltages are low, the internal AND function produces a low, which is inverted by the circle to produce a high output. Let's start the analysis with the main input at this low level. To keep better track of things, I'll give a name to the output from the first NAND gate. I'll call it mid. Mid is one of the 2 inputs of the second NAND gate. The other comes directly from the main input to the circuit. It's low. The AND function in this second gate combines these inputs into a low, which is then inverted by the little circle. The output from the complete circuit is therefore high. What happens when the main input goes from low to high? To keep things clear, I'll redraw the whole circuit again and work through the consequences of the high input. The first NAND will invert this output so the voltage at mid will be low. The two inputs of the second gate will be low and high. The internal AND function will generate a low, which after inversion will make the main output high. We can conclude that the output from this circuit will always be high. However, that's not the case. I'll illustrate what really happens by using what's called a timing diagram. This is a diagram which shows the voltage levels of a signal as time passes. In our case, I'm going to show three signals, one for the output line, one for the mid node, and a third one for the input line. The input voltage starts off low, and at some moment in time suddenly goes high. It will remain high throughout the rest of the time period we're watching. At the start of this time period, the mid voltage will be high and the output voltage will be high. It's customary to draw a dashed line down through the diagram so the reader can see exactly what happens to all of the signals at the instant there's a change. The change in this case is that the input voltage goes from low to high. The fact of the matter is that the first NAND gate cannot react instantaneously. The voltage at mid will not fall at exactly the same instant that the input voltage rises. There'll be a short delay while the circuit inside the gate does its stuff. The mid voltage will not fall until a short time later. During that delay, the output from the first NAND gate will continue to be high. I've drawn another dashed line to mark the instant that the mid voltage falls. During the delay period, both in and mid are high. They happen to be the two input lines for the second NAND gate, whose output will therefore be low. Only after the first NAND gate reacts and flips low will the second NAND gate return to its high state. The length of this delay is called the propagation time of the gate. It's typically between 10 and 50 nanoseconds, which is equivalent to 0.01 to 0.05 microseconds. A human being could never see a blip in voltage that's this short, but a circuit which follows this one might detect it and react. This issue is further muddied by another timing restriction imposed by the real world. These are the rise and fall times of the gate. The output voltage of a NAND gate does not rise instantaneously. It takes a short time for the internal circuitry to raise the voltage from low to high. Nor does it fall instantaneously. The time it takes the output voltage to change is called the rise or fall time. It's typically between 10 and 50 nanoseconds, usually in the same range as the gate's propagation delay. Let's use our NAND gates to build an AND gate. This is the circuit we already wired up on the breadboard. We used only the B gate of the chip. The other three gates were disabled. The two inputs were controlled by push-button switches and the output voltage was observed on an LED. Let's put another gate into action. Suppose we use the C gate for this purpose. Let's move the C gate over here and use it to invert the output from the B gate. I've now made that change to the breadboard. The orange wire now takes the output of gate B across the chip to both inputs of gate C. I've relocated the green wire to take the output from gate C over to the LED branch. Right now, neither push button is pressed, so both inputs are high. The fact that the LED is on tells us that the output is also high. When I press the left-hand switch, the LED goes off. Pressing the right-hand switch also turns the LED off, as does pressing both switches at the same time. This is the AND function at work. The output voltage is high if and only if both inputs are high. The NAND function was defined as not AND, in other words, as the inverse of AND. By simply inverting the NAND signal, we take a step back to AND. Next, I'm going to rewire the circuit on the breadboard so that it looks like this. Note that all four gates will be used. I'm showing the breadboard once again with the new circuit all ready to go. The purple wires are the ones that have changed from before. At this moment, neither push button is pressed, so both inputs are high. The LED is off, so that we know that the output voltage is low. When I push the left-hand push button, the LED turns on. When I press the right-hand push button, the output is once again high. But when I press both push buttons together, like this, the output stays low. The little flashes occur only because my fingers don't press down or release the switches at exactly the same instant of time. To summarize, the output is high if and only if one, and only one, of the push buttons is pressed. This truth table sets out what we saw on the breadboard. The output is high if only one of the inputs is high. This is the definition of the exclusive OR logic function. One of the inputs or the other must be high, but not both, to generate a high output. Let's see why it works this way. Start with the case where both inputs are high. Since both inputs of gate A are high, its output will be low. Having a low input contaminates gate U1D, with D for dog, and sets its output high. A low input also contaminates gate U1B, B for Bob, and sets its output low. Since both of the inputs are high, gate U1C will have a low output. We can enter this result in the truth table. In the last row of the table, both inputs are low. Let's jump ahead to gate D for dog. Since one of its inputs is low, its output will be high. We don't even have to look at gate A to see what it's doing. One low input is enough to force the output of gate D for dog high. Similarly, the one low output of gate B for Bob will ensure that its output too is high. That means both inputs of gate C are high and that its output will be low. I'll enter this into the truth table. Now let's attack the second row in the table, in which input A is high and input B is low. The output from gate A will be high. With two high inputs, the output from gate D for dog will be low. That low output will ensure that the output from gate C will be high, regardless of what gate B for Bob is doing, and into the table with it. The last remaining row is similar. This time, the low is on the top side. Once again, the output from gate A will be high. This time, it's the lower gate, B for Bob, that has the low output, and which drives the final output high. This completes the truth table for the exclusive OR function. The NAND gate is called a universal gate because it can be used to build any other logic function. NANDs can be used to build NOR gates, NOT gates, which are also called inverters, AND gates, OR gates, exclusive OR gates, and exclusive NOR gates. That's the complete list of the basic logic functions. Just a couple of points before leaving this topic. The AND function is not a universal gate. Although AND can generate a low output, it can't invert an input. The NOR function, on the other hand, like the NAND, is a universal gate. But NAND still has an advantage over NOR. The internal circuitry needed to build a NAND gate is simpler than the circuit for a NOR. Therefore, the NAND gate uses less power. If you were designing an integrated circuit which used hundreds or thousands of logic operations, you'd be using the NAND gate. For a desktop circuit, though, if you need a certain gate, you need a certain gate. The NAND gates in the 7400 chip are two-input NANDs. There are three extensions of the basic 7400 chip which are very useful. Because there are four of these two-input NANDs on a chip, the 7400 is called a quad two-input NAND. Quad is short for the number 4, like the number of sides in a quadrilateral. The 7410 chip is a triple three-input NAND. There are 3 NAND gates on the chip, which is still a DIP 14 chip with 14 pins. Each of these NANDs has 3 inputs. The truth table for 3 inputs is a simple extension of the one for 2 inputs. There are 3 columns for the inputs, so there are now 8 different combinations of highs and lows. There's only one case when the output is low. It occurs when all 3 inputs are high. In every other case, at least one of the inputs is low, and that gives a high output. In fact, the truth table is easier to remember if we say it just like that. If one or more of the inputs is low, then the output is high. Another useful variant of the NAND chip is the 7420. This contains 4 input NANDs, and there are 2 of them on the chip. Hence, it's called a dual 4-input NAND. Note that this arrangement means that there are 2 pins on the chip which are not used. Pins 3 and 13 are not connected to anything inside the chip. The notation N/C is short for not connected. You will see this often. There are lots of chips which do not use all the available pins around the case. You might well ask why manufacturers don't make a 12-pin package and eliminate the unneeded pins. It turns out to be much cheaper to standardize the package sizes than it would be to save a couple of pins here and there. Dual inline packages, DIPs for short, come in certain standard sizes: 4-pin, 8-pin, 14-pin, 16, 18, and 20-pin. There are larger ones too, but no other small ones. Now, back to the dual 4-input NAND. The truth table for each gate inside the chip is this: the output is low only when all 4 inputs are high. If any one or more of the inputs is low, then the output is high. The last NAND extension is the 7430 chip. It contains a single 8-input NAND. The pinout shows 3 unused pins. The truth table is the same as before. The output is low only when all inputs are high. If any one or more of the inputs is low, then the output goes high. One last point. Oftentimes, you'll not need all of the available inputs. For example, you might want to get the NAND value for 6 separate input lines. Well, there is no 6-input NAND. What to do? The trick is to take the next larger size of NAND, which would be the 8-input NAND in this case, tie any 2 of the inputs high. That's a fancy way of saying connect 2 of the inputs to the power supply voltage. Then, the remaining 6 inputs will determine the NAND output. I want to mention the difference between TTL and CMOS. You will often see these abbreviations. TTL stands for transistor-to-transistor logic. This was the technology used on the first real integrated circuits as we know them today. There had been a few earlier types which had used resistors in their circuits, but the TTL designs were pure transistors. At first, the transistors were of the NPN and PNP bipolar junction type, but over time they gave way to various field effect transistors, or FETs. The TTL chips were designed to operate at a standard voltage, which was chosen to be 5 volts. 5 volts is still the standard. After some time, a new technology called CMOS emerged. For the first time, metals were used in the fabrication of these chips. CMOS stands for complementary metal oxide semiconductor. CMOS could operate at a higher voltage level, and 12 volts became their standard. The most important advantage of CMOS was that it used less power, and therefore generated less waste heat. CMOS circuitry could therefore be made smaller. The first chip in the outstanding 7400 series of TTL chips was the 7400 quad dual input NAND that we've been looking at. The CMOS equivalent is the 4011. CMOS has equivalents for the 3-input, 4-input, and 8-input NAND chips in the 7400 series. Note that the pinouts for the CMOS chips are not the same as those for their TTL counterparts. The lower power supply usage of CMOS chips comes at a price. They're slower, meaning they have longer propagation delays and longer rise and fall times. In addition, they have lower output currents. That's all for now. Thanks for watching. See you next time.